That's weird. Now my notebook disappeared. I'm having a weird ghost in the machine type of day today. All right, so just to recap, so for what's on test 3, here's a nice little checklist for us, right? I'm not going to read it all again. It's all there on the page, right? Just for the video's sake. All right, I want to do a couple problems in 6 that we've covered so far. I really kind of like, I'm not sure there's anything to test on in 6.1, converting an angle to degrees. I would say you should be able to write down that reference angle table, right? So let's make sure we can do that. So reference angles. I need a theta column, a sine of theta, a cos of theta, a tangent of theta, right? And I want to use radians. So I have 0 radians, pi over 6 radians, pi over 3 radians, sorry, pi over 4 radians, pi over 6 radians, pi over 4 radians, pi over 3 radians, pi over 2 radians. And it says, even though I'm not writing radians there, I'm assuming I'm talking about radians. Unless you see degrees, I'm talking about radians. Okay. Good. What's my little sequence of numbers that I want to have memorized? Square root of 0 over 2. Right? Square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2. And some of those simplify, of course. I get a 0 here, I get a 1/2 here, and I get a 1 here. Cosine and sine have this relationship. We'll talk about what that means pretty soon. Okay? And so cosine is just going to work in the opposite direction. 1 rad 3 over 2, rad 2 over 2, 1/2 and 0. And then how do I calculate tangent? What's my identity for tangent?
Sine over cos.
Nice. Tangent of theta is sine theta over cos of theta. Right? And so for 0 radians, it's 0 over 1. That's easy. For pi over 2 radians, it's undefined, 1 over 0. Can you hear my dog? She's squeaking her pet squirrel. For pi over 4...
I didn't hear it.
You do hear it? Yeah. For pi over 4, I get rad 2 over 2 divided by itself, so that's 1. Right? And the other ones might take a little bit of work, right? So we could certainly say that tangent of pi over 6 is 1/2 divided by rad 3 over 2, which is 1/2 times 2 over rad 3, which is 1 over rad 3, right? But we will also want to rationalize it. And so we rationalize it with multiplying by 1, always in the form of that irrational number over itself, right? That irrational number in the denominator over itself. So I get rad 3 over rad 9, which is rad 3 over 3. And the last one, tan of pi over 3 is pretty simple, right? It's rad 3 over 2 divided by 1/2. And so I just get rad 3. So I guess the first thing I would ask you to be able to do is use that table, right, to find me trigs at a certain angle, right? So this is from I think this is 6.3 even. So I kind of have taught almost all the way up to 6.3. And I'm doing things kind of because the book doesn't teach it the way I would like to teach it. So I just will teach what I want. And you'll see some of it. I've already done some of 6.3. And I'm going to start teaching 6.4 today, and that's going to finish teaching 6.3. I think it's easier to teach some of the things about the properties of sines and cosines is with the graphs, but I'm a visual person. So anyway, I might ask you for this, right? Give the 6 trigs at minus 11 pi over 3. Right? So I mean, I guess this could be a problem on the test. Pretty darn easy. But I want to see the decals. What's up? You okay? And so you're going to use this table, right? You're going to use the table to do it. So is it understanding? Are you understanding what I want? I want sine of minus 11 pi over 3. I want cosine of minus 11 pi over 3. I want tangent of minus 11 pi over 3, right? And then the other 3, cosecant, secant, and cotangent, right? But let's start here. So anyway, what's my picture look like? What's the reference angle?
Negative pi over 3.
Just plain old pi over 3. All I care about is pi over 3.
Gotcha.
Yep. The negative will come in the direction I write the slices of pizza, right? So I want to cut pi into 3, which means the whole thing into 6. This one is hard to do because you can't include the y-axis. I don't want you including the y-axis, but you can see my circle here, right? So I've got, and then remember, I only want the pieces, the triangles that are created with the x-axis. So that is possibly theta. There's my reference angle theta. Yes, we okay?
Makes
But
sense.
it's negative.
Correct. So now I'm going to start labeling my viable, my unreducible pi over 3s. And because I'm moving in the negative direction, I want to go this way, right? So since I'm going to negative 11 pi over 3, I want to go minus 1 pi over 3. Negative 2 pi over 3. Negative 3 pi over 3 is no good. I'm not using it. Negative 4 pi over 3. Negative 5 pi over 3. And then not using 6 either, right? So I really can just count to 11 here, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is negative 11 pi over 3 as well. Is that making sense?
Yeah, that makes sense.
Everyone okay here?
Why do we go counterclockwise and not clockwise?
I don't know. Some of the ancients decided that's what we're going to do.
Okay.
In like Euclidean geometry, which is the geometry we all took in high school, Euclid is the one who wrote the book. We know he got a lot from the Egyptians, but we decided that a positive angle would open up. And I'm pretty sure it was before the clock. So the clockwise and counterclockwise thing, that came after. Okay, so now I know all students take calculus, right? Provided that they do what? Pass pre-calculus, right? So I know I'm in the quadrant where everything is positive, right? I'm in the quadrant where everything is positive, and this is my actual triangle, right? Right? Are you with me here? The right triangle, right? It's got to be formed. The angle has to be formed with the x-axis and the hypotenuse.
Okay.
So now this is pretty easy. Sine of minus 11 pi over 3 is now positive sine of pi over 3. Where am I getting the positive piece from? The quadrant. Where am I getting the pi over 3 from? From the reference angle, right? This is from the quadrant. This is my reference angle. And then from my table, what do I have? Rad 3 over 2? So cosine of minus 11 pi over 3 is positive. Cos of pi over 3 is 1/2. And tangent of minus 11 pi over 3 is positive tangent of pi over 3, which is rad 3 over, I'm sorry, rad 3, right? Is that right? Yep. Pretty easy, right?
Yeah.
Yeah.
Can you just explain how you find the reference angle?
Yeah. I just look at the angle and decide pi over 3. So it's basically it's pi over that denominator is the reference angle.
Right.
Let's look at one from 6.2. Oh, Sean, rational, polynomial, and radical square root. Sorry, I just saw the chat there. I'm just opening up a problem in 6.2 here. Give me 1 second. So I like problem 6.2, number 41 to 64. Number 41 to 64. I don't like anyone with degrees. I'm not asking you anything with degrees. Okay. So when I say 41 to 64, there's a couple there with degrees in them. So I guess you could first convert them to radians if you want to practice with that. So I'm just going to write down a couple problems. But in 6.2, there's not really anything in 6.1 that I can ask you about. Okay. In 6.2, I like number 41 to 64. That's a 41, believe it or not. Number 41 to 64. Okay. So definitely try a bunch of those. I mean, 41 to 64 kind of simple, but it's fine. So this is number 43. 2 times the secant of pi over 4 plus 4 times the cotan of pi over 3. So I need 2 circles here. I need 2. Sorry. I got an email from the dean. He's not coming Monday to our class.
Let's go.
He's going to come Wednesday instead. Okay, so here's our problem. I need 2 circles. I need one cut into 8 and one cut into 6. Does everybody see why? No, I don't. I don't even need it because it's right from my reference table. Sorry. Shut up, Robert. Sorry, but I don't think in secants or cotangents. I think in sines and cosines, or sometimes even tangents. So I really want to see this as 2 over the cosine of pi over 4 plus 4 over the tangent of pi over 3. Right? Does that make sense? I don't think in terms of the three other. Most of the time I only think in terms of sines and cosines. So, but in this case, it's okay for tangent because it's on my reference table, right? I want to use that reference table as often as I can. So I've got cosine of pi over 4, right? It's rad 2 over 2. And I've got tangent of pi over 3. That's just rad 3, right? And I want to simplify this. I'm always going to try and have a single fraction as an answer if I can. So this will give me what? 4 over rad 2 plus 4 over rad 3, right? And so then I'll rationalize, right, with rad 2 over rad 2. Is everybody okay here? So I've got 4 rad 2 over 2 plus 4 rad 3 over 3. And then I'm just going to get an LCD, right? So times 3 over 3 times 2 over 2. So I get 12 rad 2 plus 8 rad 3 all over 6. It looks like I can factor out a 2. Oh, I can factor out a 4, right? So I'll factor that out as well. 4 times 3 rad 2 plus 2 rad 3 all over 6. So it looks like I get 2/3, right? So 2 times 3 rad 2 plus 2 rad 3 all over 3. And there it is. It's not the trig that's difficult. It's the arithmetic. And you're going to see it's not the calculus that's difficult. It's the algebra. When you're in calc, you're trying to always write every answer as a completely factored fraction. Single factored numerator, single factored denominator. No fractions within fractions. All for the purpose to find an elegant derivative, which is our slope machine, and for other tests that happen after you learn how to find derivatives. Let's do another one from this section. This is easy, isn't it? It's going to be an easy test. It's going to be an easy test. Oh, the other one we did was just like the one we just had. Let's do one of those anyway. Let's do the number 48. So this is number 48 and 6.2. And it just says find me the 3 trigs at 5 pi over 6, right? So if theta equals 5 pi over 6, right? Find the 3 trigs. The book says 6 trigs, but who cares? I know you can do the reciprocal of things, right? So we want to find sine of 5 pi over 6, cos of 5 pi over 6, tangent of 5 pi over 6. So what kind of circle am I going to draw? How many slices in my pizza?
12.
12. I'm always doubling the denominator, right? So I'm always doubling that denominator. And it's these 2 slices that are the most important to me because they will give me 4 triangles with the x-axis, right? So I do have another slice here and another slice here. Everybody okay there? I like to say it as cut pi into 6, but pi is half the circle. So cut pi into 6, which means the whole circle cut into 12, right? And then label the bow ties. All right, pizza and pasta is what I'm talking about here, but I want those, only the triangles that are created with the x-axis and the hypotenuse, right? So I've got 1 pi over 6 here, 2, 3, 4, 5 pi over 6, that's the one I need. All students take calculus. It's also all school teachers curse. All school teachers curse. Hopefully not in the class. I think I have a couple of times, but so all students take calculus. So I know I'm in the quadrant where only sign is positive, right? So I'm going to have a positive sign here, right? And I'm going to have a negative cosine here, right? Is everybody with me? And a negative tangent here. And what's my reference angle?
5 over 6.
Nice. Pretty friggin' easy. And now what's my answers? What are my answers now? Sine of pi over 6 is 1/2. Cos of pi over 6 is minus rad 3 over 2. I'm just using to reference that table, right? Tangent of pi over 6 is rad 3 over 3. And of course, I'm adopting the sign, the SIGN, from the quadrant I'm in. Right? I'm adopting the SIGN from the quadrant, the plus or minus, right? Sean, I don't have the chapter 6 homework up there yet. I'm planning on having it done today, this afternoon or so. And I know most of you owe me old homework anyway. Cool. I think we're ready to move on to 6.4, graphs of sine and cosine and properties of the trigs. So I'm kind of mixing them together a little bit. So but we're doing 6.4 today. It's kind of 6.4 and 6.3 together. I just think it's easier to talk about the properties of the trigs with the graphs. It's easy to see the domain. It's easy to see the range. It's easy to, you know, it's, you know what I mean? So, graphs of sine, cosine. I might even do tangent today, but I'm not going to do secant or cosecant or cotangent. And tangent. And their properties. I'm not going to ask you just to graph sine function, but I need you to understand what the graph of a sine function is, so I can do the tough graphs, right? It's the tough graphs that are going to show up on the exam. And of course, you can verify everything in your calculator, right? So there's no issue there at all. So let's take a look at what the graph of a sine function is. I'm not quite as prepared as I'd like to be today. I'm sorry about that. But I have to go grab a Sketchpad file that I wrote, I don't know how many years ago. It would be nice if you all could create one of these things using GeoGebra. Not GeoGebra. Yes, either GeoGebra or Desmos. It'd be pretty cool if someone came up with one of these on Desmos. Now, I know one exists already. Okay, so I'm not asking for that. I'm asking for you to go through the process of how do you build something like I'm going to show you. Okay. Sign shifter. Sign height. This is what I want, I think. So I'm opening a program called Geometer Sketchpad. It's not free. I used to teach high school geometry with this in Los Angeles, California. And so I just had to open the sketch I just downloaded. Where is my downloads? And so this is my sine triangle height. Now, if you remember for me, when we use the unit circle, we could talk about sine much simpler, right? We could talk about the sine function, right? When I used the unit circle, which meant the radius was 1, and I had a height of y and a base of x, I got sine of theta was actually just the height of the triangle, right? Yes, you agree with that based on this picture?
Yes.
We got cosine of theta was the base of the triangle, and we got tangent as what?
As the hypotenuse, the one.
As the slope of the hypotenuse.
Ah,
These little things, these little subtleties of all the trig stuff is what we are calling properties. Like we had the properties of logs, right? We had the translation, we had the inverse properties, we had, right, you could expand or contract the logs, and then the change of base formula, right? So anything I'm kind of mentioning about any of the trigs is what we're calling, or the book is calling, properties of it, right? So since the sine is simply the height of the triangle if I use the unit circle, and I still kind of have to convince you if I don't use the unit circle, it still will come out the same way. I can look at my sketch here and have it. I want to move everything. Nothing will move. Sorry. Oh, here's my triangle. So I'm taking that triangle from the unit circle, right? And I'm moving it down onto my x-axis. Okay. So let's just. Where's my animation point? Sorry. Oh, animate. Here it goes. So you can see my triangle moving in the circle, and that projected triangle down onto the graph, and I'm tracing the height of that triangle as I go. And there's my sine curve. Excuse me. So the curve of the sine function, and I'll usually write down at one period, one repeated pattern is fine. So you know it's going around the circle again, so it's just going to keep going, right? So, but we want to always be thinking about the 4 quadrants, and I call them quarter steps, okay? So I want us to be thinking about the 4 quadrants or quarter steps. And so my quarter steps are coming from, pi over 4s, right? So I've got a pi over 4, 2 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, right? Oh, I'm sorry. Pi over 2s. Right? Each quadrant is pi over 2, right? 90 degrees is pi over 2. So then another pi over 2, and then another pi over 2. And I'm back to the beginning of the circle with the 4th pi over 2. These are my quarter steps, and this is important for me to be talking about when I do the more difficult graphs. I should know that I'm going to always split this sine curve into quarter pieces for the quadrants, right? So this is quadrant 1, quadrant 2, quadrant 3, quadrant 4. And we saw that the height of the triangle starts at 0, right? At 0, the height of the triangle is 0. At 90, the height of the triangle is 1. At pi, the height goes back down to 0. At 3 pi over 2, it goes down to -1, and then back to 0. And there's my sine curve. So any kind of wave, and this is a fascinating thing to me, but maybe not to you. Any kind of wave is related to what shape?
Sound.
What do you mean?
This is can you see this is a wave? A wave, right?
Yeah.
Related to what shape?
Infinity.
Infinity is a concept, right? Not a shape. Oh, I know the symbol. I like,
Rectangle.
yeah, I like the symbol for the car. What shape am I relating this wave to?
The unit circle?
A circle, a circle, a circle.
Ah, there we go.
Yeah, and it's kind of freaky if you think about what's controlling our tides.
Ah, the
The
moon.
moon. There's all kinds of weird. Now, the ancients used geometry as philosophy, and so the circle represented God, and the triangle, the square is human. So you've probably seen this Michelangelo drawing before, where you have a circle and a square, right? Something like that. And if the human is just standing with his or her arms out, right? Our wingspan is usually the same as our height.
Oh, right. I think that's Da Vinci.
Oh, it's Da Vinci, yeah, right. And then he moves into the pentagon, right, to be out as a
Right.
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 And this is a famous problem called circling the square. To draw a circle and a square with the exact same area is impossible. Hasn't been done yet. And so this is related to this, connecting human to God. So, but anyway, this is our sine function, and we can get a lot of the properties right from it. It's going to just keep repeating, right? If I keep going to the right, it's going to keep repeating like this, right? If I go to the left, it's going to keep repeating like that. So, and of course, moving to the right is moving counterclockwise in the circle. Moving left is moving counterclockwise in the circle, right? And I can see my quadrants keep repeating too. So what's going on over here? What quadrants do you see there? What's this green quadrant here?
Four.
Yes, 4. That's quadrant 4. Right? Because it has to go 1, 2, 3, 4, 1, 2, 3, 4, 4, 3, 2, 1, 4, 3, 2, 1, right? Depending on which direction you're going. So there's the sine wave. So obviously, what's the domain?
All real numbers.
Yes, all real numbers. What's the range? What's the highest I get to?
1.
Yep, so minus 1 to 1.
Two.
Minus 1 to 1 for the range. Nice. What's the period? When does it start to repeat? How long does it take? 2 pi is the period. And of course, our quarter steps, right, are n pi over 2s. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. You're going to see the reasoning behind me wanting to do sequences and series come back into play here. You're going to start to see sequences of quarter steps, right? Because you're always adding 90 degrees, right? So if you're always adding the same thing, I should have a nice little sequence for that. So our ultimate goal is to be able to graph this guy, plus or minus a times the sine of b times x minus c, all plus d. And we're gonna deal with those letters in order. This is the tough question from this section. So we're going to deal with those letters in order. Handle the plus or minus. Handle the a is the amplitude. Right. This is my amplitude, which is really just the radius of the circle. and B is the frequency. And who had said they did some frequency stuff in your 0098?
Me.
Nice. Yeah, cool. Diego, nice. And then C is my phase shift, but you can already tell it's a shift where, because of where it lives. What is it a shift of?
At E.
No, where on the graph?
Left or right?
Exactly, and opposite, right? And then finally, this guy is called my midline, but you already know it's the shift up or down, right? So we're going to be really focusing. If you remember go ahead, Diego. What were you going to say?
No, nothing.
Okay. So if you remember what we were focusing on with the mother functions, we were focusing on that 1x1 square. But now we're going to have this rectangle is going to be our focus. I'm going to basically graph that rectangle first, right? And then put in my sign. And right, I know sign starts at 0, goes up, comes back down to 0, comes down to -1, back to 1, right? I'm going to remember that shape for sine curve. And you'll see a lot, if you take me for calculus, whenever I do a problem with a sine curve, with a sine function in it, I'm always quickly doing, my quarter step, down, up, down, down, up, and I'm always looking for that shape real quick whenever I have to think of something, right? And look at this, all students take calculus. All means everything is positive, so sine is above the axis. S means sine is positive, so it's above the axis. Tangent means everything else is negative, so sine is below the axis. And only cosine is positive, means sine is also below the x-axis, right? We're trying to connect all these little things. Nice. Let's take a look at the cosine curve, okay? So these are the properties we want to memorize them.
Sorry, Professor. I don't know if I'm tripping or something, but isn't this like the equation? I remember also seeing it in my physics class when we were looking at sound.
Exactly, sound waves. Exactly.
Oh,
Exactly what a sound wave is. And if you ever noticed a speaker, like a musical speaker, right? It rotates. Okay? A speaker rotates. As the vibrations come out, it makes it rotate. It makes it so there's a fantastic connection to a point moving around a circle as actually being a note. A single point moving around a circle. So if I played a single point on my guitar through the speaker, it would be moving as a circle.
Okay.
And I know you're doing physics, right? That's what you're studying, right?
Yeah.
Nice. Yeah, I did a presentation on campus a little while ago. Actually, it's probably 3 years ago now. Where I connected music to the circle. Let's see, I think you can still watch it.
Oh, that's pretty cool.
Yeah. Let me see if I can show. Where it is. YouTube. Robert Kuhar YouTube. I think it's like I only have our videos up there right now. I usually just delete them every semester. But I have that presentation up there. So what I'm doing in this presentation is I've got my guitar plugged into an amplifier, Amplitude, same thing. And I got a little piece of glass on the speaker at an angle of 45 degrees. And I'm shining a laser onto the glass as I play different harmonies. And There it is. Math and Music, Part 1, Part 2, Part 3. I was in the planetarium on Tacoma Park showing this. And so if I play a single note, you see a circle onto the screen. If I play two notes, an octave apart, that's one note going, let's say speed 1, and another note going speed 2. This is where the frequency comes in. So you've got one going twice as fast as the other, and it gives you it gives you the shape of an octave, an 8, the infinity symbol. So it's pretty cool stuff.
Okay, I'll check those out.
Yeah. I don't know who. I haven't watched them. I didn't do the recording. I don't know who did the recording, but it's pretty cool stuff. This is the stuff that we wish we could teach in class, but there's just no time. You know, the stuff that makes math really cool. I know it's hard to hear that, but what? All right, let's take a look at the cosine curve. So cosine, right? Cosine. Oh my, something just happened. I'm probably losing memory from the sketchpad thing. Let me shut this off. Sorry. This Surface Pro has got a very small brain, so it can't handle a lot of things going at once. What? Just my girlfriend just said, just like the teacher. Thanks, EJ. Love you too. So y equals cos of theta, right? So I just want to give you the quick quarter step view. 1, 2, 3, 4. There are my quarter steps. I know I'm going to have a bound from 1 to -1, right? Because it's the same circle here we're talking about, right? And remind me, I have to tell you that it doesn't matter if it's a unit circle or not. I'm going to get the same graphs. And so for cosine, I'm starting at 1. So the cosine one is pretty easy to remember because I get the I get a smile kind of look there. And you can see that if I just continued it a little bit more, you can still see the sine curve, right? Can you see the sine curve? So cosine and sine are exactly related like that, right? They're just a shift off of each other. So there's my cosine curve, but let's understand it. Cosine is really x, right? Cosine is giving me the base of the triangle. And when I start at an angle of 0, right? When I start at an angle of 0, my base is 1. It's all the way to the end of the circle, right? And then as I move, right, what is happening to the base? It's getting smaller. When I get all the way to the vertical, there is no base anymore. That's my 0 here, right? And then just follow that base around. It's getting bigger again, right? And there it is, all the way to the end. It's getting bigger again. But it's in the negative x direction, so it's -1, right? Are you following me with that, the cosine curve?
Yeah.
Nice, Grace.
Yeah,
There you go.
no.
Yeah, on hell. Brandon, yes. Nice. So we really have the same properties here for the cosine curve, right? We've got a domain of all reals. And remember, it keeps going, right? It keeps going. It keeps going both directions, right? It's just that constant wave. The range is -1 to 1, inclusive. What else? What else did I have on the other one? I forget. Oh, period. The period is again 2 pi. Right? And the quarter steps are the same. I guess it's interesting to look at the zeros of sine and cosine. Those should be interesting. But we want to be able to, at any time, quickly draw out this mother cosine or sine curve or cosine curve, right? So the sine curve, 1, 2, 3, 4, right? And I might as well, I'm going to keep going a little bit, but I know my sine curve starts at 0, goes up, back down, right? So there's the sine curve. And then if I continue it, right? So there's that sine curve. It's interesting to look at the zeros here. So purple is going to be my sine curve, y equals sine of theta. And I'll do green as cosine. Cosine starts here, down to here, down to here, up to here. So there's my cosine curve. So look at where the zeros of the purple curve are. At 0, at pi over 2, I'm sorry, at 0, at pi, at 2 pi, right? This is 4 pi over 2. So you can see they happen at every pi, right? So sine of theta equals 0 at k pi. So, and k is k belongs to z. Z are the integers, right? Z is ... -3, -2, -1, 0, 1, 2, 3, ... right? So at every integer coefficient of pi, 1 pi, 2 pi, 3 pi, 4 pi, sine will be 0. It'll hit the x-axis. Is that making sense?
Could you explain the k part again?
Yeah, k is just a number, right? And the numbers are obvious. -1, 0, 1, 2, all the integers. Positive and negative integers. So for example, right here, sine hits 0, and that's -1 pi.
Okay.
So at 0 pi, at 1 pi, at 2 pi, at 3 pi, at 4 pi, sine is going to hit 0. When's cosine going to hit 0? So looking at the green. Okay, but the first time it hits is right here, right? And remember, that's if I just clean up my graph a little bit here.
Oh wait, yeah, pi over 2.
There you go.
Right?
Pi over 2, and then 3 pi over 2, and then 5 pi over 2. So odd pi over 2s. So at 2k plus 1 pi over 2. If you remember, we got that odd sequence in chapter 8, right? We had 1 pi over 2, 3 pi over 2, 5 pi over 2, right? So I'm just getting that sequence for 1, 3, 5, and that one was a 2n plus 1. It was a 2n minus 1, but either one works. Now let me make it 2k minus 1. Right, just getting that sequence for 1, 3, 5, 7, 9, right? So chapter 8 will come into play in a couple of aspects of trig. You don't have to do it, but I just think it's a nice little connection. You could just figure it out a long way instead of have all these little secrets from things in the sequences and series. Well, tangent is the next one to show, and tangent has a period of pi. If you think about that unit circle, and you think about the slopes, right? Here's an infinite slope, and negative slope. What am I saying here? Yes, and then back to infinite slope, right? So I get half the way around the circle and my slopes start to repeat, right? So the tangent graph as from minus pi over 2 to pi over 2, right? There's my tangent curve. And you can see right around pi over 2, it's going to a vertical asymptote, going to an undefined slope, right? So there's a vertical asymptote here at pi over 2 and minus pi over 2. So the tangent curve is a little bit different, not much different. Y equal tan theta has a period of pi, right? From minus pi over 2 to pi over 2 is pi. It has a domain of x does not equal odd pi over 2's, 2k minus 1 pi over 2's, right? With k as any integer. The range is infinite, right? And then again, it repeats, right? There's another one here and another one over here, right? These things are always, right, always repeating forever and ever. Just remember, because I'm just going around a circle. And I'm going around a circle. I can go around a circle both ways. Nice. That's all I want to do today. So you're reading up to 6.4. You should be able to do any problem they ask you to do. There are some things in there that I didn't talk about, but I think your trig teacher did. And so I'm okay with that. I'm okay with letting you do a little research there and reading in that chapter 6. You should still have your book from trig. So you would have covered all of the stuff that I've talked about. In fact, more. There's some of 7 that you talked about inverse trigs. Diego, is that fair to say that you talked about inverse trigs in your trig class as well?
I don't remember.
Arctangent, arcsine, arccosine. Sound
No.
No?
Oh, I remember those.
Yeah. So that's chapter 7. So there's a little bit of 7, but so you're going to see. I think this is really everything you've talked about in 098, and that's in our chapter 6. And then I'm going to the very next chapter, section of 6, you'll see is difficult. Okay. So then I'm extending some of the stuff you did in your trig class. Chapter 7 will start with inverse trigs, but I'm going to extend it again. It's going to be a little bit more in depth. And so then you will, and then we get into the advanced trig stuff. All the rest of 7 and 8. Okay. All right, that's it for today. Have a great weekend. Get some work done.
Have a good one, Professor.
Thank you.
Have a good weekend.
Thank you.